Okay, so let me talk here. Basically, we talked about all of this, I think. Maybe some in more detail than others. I think these are some of the guiding principles that I have in mind. Maybe they're obvious after this, but data-centric system design and intelligence spread around as opposed to processor-centric system design. Basically, we're centering everything around traditional computation units today. That may not be a good idea. I think we need better cooperation across layers of the system, from the devices to the architectures to the system. And we need to carefully co-design components on layers. I think this is obvious in memory controller, memory interface, but that's true for programming and memory interface. There are a bunch of these different interfaces. I think we need better, richer, and more expressive and flexible interfaces for this. Of course, we need to ensure that the average programmer Joe doesn't go crazy. But I think there are other mechanisms. Once we have these interfaces in place, people will take advantage of it somehow. I think the other principle is obvious, maybe better than worst case design. Essentially, in memory today, a lot of things are optimized for the worst case. And worst case is determining the common case today. I mean, we know in processors that this should not be the case, but in memory we should really do it more aggressively. And clearly, it's another principle, heterogeneity in design. Again, this is obvious perhaps, but in memory we're discovering it more and more. We want more heterogeneity, heterogeneous refresh rates, heterogeneous memories, heterogeneous latencies, but we're not there yet. And it enables a more efficient design clearly because there's no one-size-fits-all, right? I think I have a more compact form of it. Data-centric design, all components intelligent, better cross-layer communication and better interfaces, better than worst-case design, heterogeneity and flexibility and adaptability. But I think maybe most important thing is open minds in memory. I think memory is a bit interesting because somehow the DRAM industry has constrained itself into a position where they cannot move a lot, or they think they cannot move a lot. And that's very bad for innovation. Because if you really want to innovate, you want to be a lot more flexible, right? I think partly this is mindset, maybe partly this is business. I don't buy it's mainly business part. I think it's really, maybe the business demands have somehow put the industry into a vicious cycle where they now think like this as opposed to thinking like this. Okay, I think basically the open mind is a big part of it, but I'd be happy to talk about that more. So I think data-aware architecture is something we didn't talk about, but maybe we need to also understand what we can do with the data. Basically, today we have data, but we don't know much about the data. Well, maybe we know much about the data, but we don't communicate it to the underlying hardware. For example, I think a data-aware architecture makes use of different properties of data to improve performance, efficiency, and many other metrics. So these are some characteristics of data that I believe don't get communicated nicely to the underlying hardware. Programmer may know some of this, may not know some of this. Compilers may know some of this, may not know some of this. Compressibility, approximability, locality, sparsity, criticality of some particular computation, access semantics. So we have this rich information that we know or we can figure out, but in the end, what we communicate to the general purpose hardware at the bottom is memory addresses and instructions. In some very specialized cases, you have these prefetch instructions or eviction instructions from the caches, but they're very specialized. We don't have a general interface for this. So I think essentially this higher level information is not visible to a hardware except in some very specialized cases. And we wanted to actually fix this problem. And we've been working on an interface we call XMEM, expressive memory, that can communicate some of these higher level program semantics in a general purpose and flexible manner. Of course, in specialized systems, some of these are, if you're designing a domain-specific architecture, for example, maybe you're communicating some of these. But we want it to be much more general purpose in the communication of these. And I'm not going to talk about this, but I think I'm very interested in this direction. And we have a huge table in this particular paper that says you could enable all of these optimizations in very different problems if you actually communicated more information from the software into the hardware and the system. Compression is one example over here, but I don't want to go into more detail right now since we're already out of time. And we actually employed this in a specialized case in collaboration with NVIDIA. Essentially, this is expressive memory concept employed in GPUs with a locality descriptor. Basically, the programmer specifies the different types of locality that you have in a particular computation that you have in a GPU, and you communicate it to the hardware, and the hardware takes action accordingly. And I don't want to go through the action, and I don't want to go through the program interface. If you're interested, you can take a look at it. And NVIDIA is actually taking this and implementing in their products going forward. Of course, GPUs are a domain where you could easily go through this, but maybe general purpose architectures can take advantage of this as well. Okay, I'm going to skip this one. Let me conclude. I think conclusion is interesting because this is the most fun part of the talk for me. So some very famous architects said this in the past. Architecture should be based upon principle, not upon precedent, not upon what comes before. Can anybody guess who this is? He's not a computer architect. It's actually a real architect, Frank Lloyd Wright. And he didn't design this because this is more precedent based. This is actually not bad, right? I don't mind living in there. But he was more principle based, and he designed this instead, which is falling water, which is masterpiece. And it has many different characteristics. It's essentially on a waterfall. This used to be one of my assignments that I gave to the students when I was at CMU giving these lectures. And I said that you should go there and exercise your creative thinking. And clearly this is based on some principle. It's actually the waterfall, the building imitates the structure of the waterfall. And this is organic architecture, and you can read about it. Now that I'm in Zurich, I use different examples. You have these in Europe all over. This is a precedent-based design, I think. It's a train station. It works. It's not bad. But it's not like this. This is Stadelhofen, Bahnhof Stadelhofen in Zurich. It's based on some principle. This picture doesn't do justice to it. Once you go here, you can see this structure even better. Of course, people paid more cost to it, right? We should talk about that also. There's some cost that came with this principle. And the Kaufman family who wanted this at some point had to tell Frank Lloyd Wright, you should stop. We're not paying you anymore. So this is new. This is old technology. This is old technology. You can live with it maybe, but maybe it's wasteful or whatever. This is new technology. To transition to it, you have to pay some cost. This is processing in memory maybe. Okay, so in Zurich, going back to Zurich, this is the more principled design. This is another more principled design. If anybody is from Lisbon here, you would recognize this in Portugal. This is the GAR over there. This was the first place I went to when I visited Lisbon, because it's very easily accessible from the airport also. And this is also based on some principle. There's another place in Valencia, if you've been to Valencia. Same architect again, similar principles. Another place. Does anybody know where this is? Okay, it's in New York, right? Oculus, yes. Yeah, essentially it's also a train station, it turns out. The previous one was not a train station. But it's from the same architect, and I use this as an assignment, and amazingly people go there and send me pictures. I teach this large freshman class in ETH, and I think I got 20 or 30 pictures from Oculus. Apparently New York is a good place to visit. But if you ask New Yorkers, when this was being built, it cost New Yorkers about $4 billion according to Wikipedia. And there was a lot of controversy, a lot of criticism. Now the transition to new technology is complete, meaning that this exists. People go there and people enjoy it inside, right? Because they forgot about the cost. To be able to transition to a new technology, you have to pay some cost. It doesn't come for free. And I think none of the things that we've discussed is going to come for free. Some of them may come at low cost, but processing in memory is not going to come for free. Flash memory didn't come for free. People invested a lot of money into flash memory, and DRAM didn't come for free also. By the way, this is the architect, Santiago Calatrava, who is a PhD in civil engineering from ETH. And this is his principle, which I'm not going to go into. So basically, I don't claim to have the overarching principles for computing. And maybe we don't have only a single principle in this case. I don't believe in architecture we have single principles also. That's why we have all these famous architects that are doing different things, right? In computing also, I think, I know that there's not a single principle. And definitely processor-centric architecture is not how nature operates, I think. Maybe in localized fashions it operates that way, but there's a broader picture that we're missing. Actually, I studied psychology at a time when people still thought that computing is a good paradigm for understanding humans. I don't think people think about it that way. So because computing was so powerful in the late 1900s, early 2000s, people were thinking, okay, we can use this as a blueprint for understanding human behavior. And I think that paradigm failed miserably, because somehow humans are completely different from computers. Maybe if we understand, maybe we can, if we design some different principles in computing, maybe more data-centric architectures, more distributed architectures, maybe computing can be a blueprint, but I don't know if that's true. But clearly we don't know the principles for computing. But if we can, I think, figure out those principles, that would be good. I've already said this actually. I'm not going to say this again. But I think we need to think across the stack. And I already said this. But I want to do a final detour, as I promised. So we talked about in-memory virtualized operations, right? It sounds like a great idea. And I said that the paper was rejected 4 times. I'm going to show you some reviews that we received. I've already shown these reviews actually in ISCA a couple of times, not just once. I think it's good to show these reviews to the community because there are a lot of graduate students who get similar reviews, and I think they should not be discouraged. Basically, this review is very interesting because this person says, very clever, novel idea, great potential speed up and energy efficiency gains. You would say this is an accept, right? But if you look at the weaknesses, probably it won't be built. I don't think this is a good criticism because if you reject papers this way, then probably all papers would be rejected, right, before they're being built, right? How do you know? First of all, how do you know? Second of all, this is not a scientific comment. And third of all, if you say it's not going to be built, maybe it will never be built because nobody thinks about it. And amazingly, people did not think about it until, I don't know, if you know of a previous paper that has these operations, I'd love to know. Then I'd be happy to do due diligence to cite it. But amazingly, people didn't think about it until we exposed it. Yeah, sorry.
Turing's first paper was also rejected.
Yeah, sure.
Very common rejection.
Reason, right? Exactly, yeah. But I think we need to change this mindset somehow. I don't know. So the paper did not appear in ISCA 2016, by the way. It appeared in Micro 2017. Okay, I mean similar comments actually. Basically, it's unlikely that something like this will be built. Actually, whenever my students get comments like this, there is this website that talks about 8 papers that were rejected that later went on to win the Nobel Prize, and I point them to that particular thing. Turing didn't win the Nobel Prize, I think, but some other papers did, and they were not published in top venues actually. Okay, so this is another review. This is a very interesting one I find. Basically, this person says, I do not find architectural motivation, even though the circuits technique, blah, 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 basically. This is a circuits paper, basically, the takeaway. The only related part is the new ISA support. Basically, you can come up with a lot of rejection reasons if you want to reject a paper. Okay. So I think we have a mindset issue. There are many other similar examples from reviews for many other papers, and we're not even talking about JEDEC yet. These standards bodies are even more crazy, I think, and political. But I think this sort of stuff doesn't have a place in science, but somehow we need to fix the mindset problem. I think we can fix the mindset problem by doing more research, education, and implementation in alternative processing paradigms. So despite all of these, I would encourage people, especially the younger people, to do more research in these areas and be more resilient. Because we need to work on enabling the better future. If we say it's not going to be built, we can ensure that it's never going to be built. I actually used this also in a previous talk recently. Does anybody know this book? Nobody? Oh, you use it in your classes, or?
No, I have just I read it, I think, early 1990s.
Okay, I see, yeah.
It's probably in my bookshelf.
Yeah. Did you like it when you read it?
It was actually very timely at the time.
At the time, sure. I think this book is actually very nice. It still has a lot of good tidbits. Maybe it's a bit older, but some of the fundamentals are there. I like a lot of things about this book. I have multiple copies, actually. But I like one thing over here. This is a very nice page over here. This is our ret holes. So whenever you present some performance analysis results, even if the performance analysis is done correctly and done and presented, it may not be enough to persuade your audience, the decision makers, to follow your recommendations. The list shown in box 10.2 is a compilation of reasons for rejection heard at various performance analysis presentations. And this person says, Raj Jain, you can use the list by presenting it immediately and pointing out that the reason for rejection is not new and that the analysis deserves more consideration. Also, the list is helpful in getting the competing proposals rejected. So he has some sense of humor also. So there is no clear end of an analysis. Any analysis can be rejected simply on the grounds that the problem requires more analysis. That's the first reason for rejection. But I like this actually because sometimes I present this, and I have the seminar course. I say that whenever we have discussions, you should be careful of these rat holes. So a workload is a rat hole, for example. You can always say, oh, you didn't test these workloads. How does it work on these workloads? That's a rat hole because that's an endless conversation. Another thing in metrics, you didn't test these metrics. Configuration, you can always look at more configuration. You need more detail. And these are the reasons, actually. I really like these reasons. Some of them are very insightful. The first one is this needs more analysis. You need a better understanding of the workload, blah, blah, metrics. I like the last one because the last one is really a mindset one. Why change? It's working okay. And that's exactly the computing systems that we have today, I think. They're working okay. We don't really have huge problems with it, except they're not sustainable and they're not energy efficient. Okay, let me show you the last one. I think people like this one a lot when I present it, and especially this is good for graduate students. This is a paper that we submitted to Micro 2013. Yes, Micro 2013. And clearly it's rejected, as you can see, and you can see the scores. Some people really liked it. 5 and 4 are large, actually. 1s are not good, 2s are not good, and this paper was rejected, as you can see. And this is a Rowhammer paper, and it was very similar to what was published in ISCA in the end. Okay, maybe Polish. We polished it a lot, but fundamental things are the same because we demonstrate in real systems. So let me show you some of the reviews. One of them says, oh, I don't care about this because it's not architecture. Okay. And it was a reject, actually. Okay, this cannot be an issue in realistic DRAM usage scenario. Okay, maybe you should think more broadly. And, okay, the paper doesn't discuss the root causes in sufficient depth. Okay, anyway, I think it's good for the graduate students to see these reviews. Yes? You were saying something?
No.
Okay. Yeah, I can keep more. I have a lot of data points, actually, in terms of the review process. I can do some data mining and show you examples of these reviews. But the paper was clearly rejected from Micro 2013. Actually, I don't have the. I should do this. I should do this for ISCA. In ISCA, where it was accepted, the reviews were very bipolar. Some of them gave 1s and 2s. Some of them gave 8s and 7s. 8 and 7 was the scale at that time. 8 was the top one. And it got accepted to ISCA. But we still got very interesting comments, actually. So we started this work in 2012, and we demonstrated this, submitted for the first time to Micro 2013. And by that time, people were making noises about Rowhammer. And because they rejected us, this video appeared on YouTube, and one of the reviewers wanted to use that as a reason for rejecting the paper. They basically said, this is no problem now. We don't want the paper on this topic, just because of that video. And that video, very briefly, I know that video, actually. I attended that conference where that video was recorded. It was in MemCon in October 2013, after our paper was rejected. So it's interesting, I think, the way people work. I'm glad the paper was accepted to ISCA, because if it was not, then I don't know. Anyway, it wouldn't have the impact that it would have, perhaps, right? Okay, another one here. The same reason, basically. It appears to be a well-known, and solutions have already been proposed by industry to address the issue. Interesting, because we actually referenced some of those patents that were filed, because we worked with Intel to actually look at some of those solutions as well. So we clearly referenced in the paper that industry is aware of the problem, and there are these patent applications that were filed concurrently with when we actually started the research, and they're all in the paper. So it's amazing, but some of the reviewers were more open-minded, and they actually got the paper inside ISCA, and as a result now you can read the paper. Otherwise it could be an archive publication with probably less impact. Okay, I think this is a suggestion that I presented to reviewers, actually, in a talk that I delivered at ISCA. But I think we really need to fix this problem, because I think some of the time I believe that we're really blocking the scientific progress for non-reasons whenever this happens. And I also presented these slides at ISCA, actually. We need to fix the reviewer accountability problem. I think the reviewer system is somewhat broken. Maybe it was broken as early as Turing, that's true. But I think it's becoming worse, perhaps, right now. And I think there are a lot of double standards in the process that really spoils the, I don't want to call it the game, but spoils the scientific progress. Anyway, I think on a more positive note, people who are really excited about something, they should follow their passion. They should not get derailed by naysayers who come up with these random reasons, as you can see. I was fascinated by their use that said, okay, this is not a problem, reject, and then this is a known problem, reject. And then in between, it was not known beforehand, right? I think that's a naysaying mentality, if not something more malicious. And I think being resilient is important. And I think focusing on learning and scholarship is important. This is again from the talk that I delivered. Okay, I think I'll finish with this one. Okay. I'm happy to take more questions. Yes, please.
I have a question on hard real-time problems, because we talked a lot about improving things, but not so much into hard constraints. So when we complicate the memory systems, we add some variations at runtime usually, and you work also on these kind of problems. So strongly predictable systems.
Yeah, exactly. I think we wanted to provide strong memory service guarantees. Maybe not with an extremely hard real-time focus, but we were more softish real-time. But I think it's really important to solve those problems. But I think we need to provide those while also having high performance. So I think there still needs to be more research done in hard real-time while reducing the latencies. I think reducing the latency actually helps in that case, but maybe you want to reduce the latency variation as well, or maybe disable some of those parts that lead to those latency variation, right? Maybe you just use those parts that are more lower latency if you know those latencies. Today you don't have that option again. And I believe actually if you're more data centric, your latency is already lower, and maybe the real-time problem becomes better, easier, potentially. I really think security problems become better if you actually are executing near data and not moving data all around the system. Because a lot of the security problems appear because data is cached, data is visible, somebody can probe the data. If you can keep it there and keep it secure right there, maybe it's better. But I think real-time may have something similar. But I haven't seen a lot of work in the real-time community that looks at in-memory processing, for example, or that assumes you can reduce the latency significantly and see what happens. Maybe there's more work to be done there. Sure. Yes?
Does not adding software to the memory unit decrease the security, because then you have additional attack layer?
If you do processing in memory.
Yeah, then you have software in the memory and there's an additional attack layer.
Yeah, so you can think of it that way also. That's true. Yes, I think I agree with that. Now you have some more processing across the entire system, but maybe you can limit some functionality for security inside the memory. I don't know. I think there needs to be more research in that area, basically. But I agree with that. It's possible that you could be vulnerable to some new attacks that people have not considered before, because now you're doing processing inside the memory. Any other thoughts, questions? Okay, well, thank you for staying until this late in this beautiful island.
Thanks for your
Yeah.